Hello everyone, I'm Pengpeng Liu from the Chinese University of Hong Kong. In this presentation, I'm glad to introduce our work, Self-Flow, Self-Supervised Learning of Optical Flow. In this work, we present a self-supervised learning approach to learning optical flow from unlabeled data. Our method distills reliable flow estimations from non-occluded pixels and uses these prediction as ground truth to learn optical flow for hallucinated occlusions. Next, I will use a simple example to explain our main idea. Suppose that initially P1 is non-occluded from the first image to the second image, and P1 prime is its corresponding pixel. Because that P1 is non-occluded, our NOC model can estimate it accurately using photometric loss. NOC model here means non-occluded model. Then we inject random noise to cover P1 prime, and P1 become occluded from the first image to the new second image. Because that P1 become occluded now, our OCC model cannot estimate accurately using photometric loss anymore. OCC model here means occluded model. Luckily, we have estimated optical flow of P1 with NOC model. Then we can distill reliable flow estimations of P1 to get the flow learning of OCC model. Note that the guidance is only implied to those newly occluded pixels, such as P1 and P2. During training, we only imply photometric loss LP to NOC model. For OCC model, apart from LP, we also imply LO to cope with occluded pixels. Then we use the pre-trained OCC model as initialization and fine-tune it with ground truth optical flow. Our self-supervised pre-training removes the reliance of pre-training on synthetic datasets. Next, I will show you our quantitative results. Our unsupervised methods outperforms all existing unsupervised methods on all datasets except central clean. Our unsupervised methods even outperform several fully supervised methods. Our fine-tuned model achieves state-of-the-art results. Note that existing state-of-the-art supervised learning methods rely on pre-training on synthetic data. This is the first time that a supervised learning method achieves such a high performance without using any external labeled data. Our fine-tuned model on Centile achieves EPE equals 4.26, outperforming all submitted methods, and until now, it is still ranked first. Next, I will show you some qualitative results. First, I want to show the effect of our self-supervision strategy. When self-supervision is not implied, the estimated output flow looks noisy. It is because NOC model lacks the ability to predict the optical flow for occluded pixels. After implied self-supervision, the results are much smooth. These are results from the KT datasets. This is a video comparison. These are results from the Centile dataset. This is also a video comparison. Comparing with current state-of-the-art PWS-NET, our fine-tuned model estimates optical flow with more accurate data. For example, the finger here, and the leg, and the stick. To demonstrate the generalization ability of our model, we further show our optical flow estimation on real-world videos from Davis dataset. The second row shows our unsupervised results, and the third row shows our fine-tuned results. Then comes our conclusion. Our code is available on this website. That's all. Thank you.
Welcome to my talk, taking a deeper look at the inverse composition algorithm. This work is done as an internship project in Autonomous Vision Group, MPI, and also collaborated with Georgia Tech. The Seminar-Lucas-Canali algorithm is a widely used image registration tool in computer vision. It recovers the motion transform by minimizing the photometric residual of a warped image to the template. One classical solution to the objective is the inverse composition algorithm. In each iteration, giving the residual of a warped image to the template, it solves the incremental transformation of origin-perturbed template to the warped image, and it updates the warping with inverse composition iteratively. We often use a weight matrix to cope with the influence of the outliers. We also often add a damping regularization to cope with the bad initialization. Despite being popular, the inverse composition algorithm has a number of important limitations. The objective assumes photometric consistency, which may not hold in practice. High-frequency noises or textures may fail the linearization step and makes the resulting Jacobian less informative. The weight matrix is often derived from the classical robust MS meter. In this formulation, the weight of a datum depends on the point residual, which may not address context in the high-order information. Adding proper regularization is also a non-trivial task. One common way is to adjust the value damping using some heuristic rule like the trust region method, but this heuristic rule may not find an optimal solution. In this work, we will take a deeper look at the inverse composition algorithm and see how we can address these challenges using learning. First, we propose a two-view feature encoder network. It learns the feature space for the residual evaluation. The learned feature also makes the resulting Jacobian more informative. Second, we propose a convolution MS meter to learn the weight matrix using both views of features. The learned MS meter can more effectively leverage the context and the high-order information to weigh the samples. Third, we propose a trust region network to more accurately and effectively approximating the trust region behaviors using learning. We use this learned damping parameter to replace the classical heuristic damping in the Levenberg-Marquardt formulation. To summarize, we make three contributions, with each as a learnable module, and we follow the same computational graph as a classical inverse compositional method. We propose a two-view feature encoder to replace photometric residual, a convolutional MS meter to replace the traditional MS meter, a trust region network to learn better damping regularization. All operations are differentiable, and we train all the modules end-to-end using the ground truth motion transform. Like the classical inverse composition algorithm, we also perform our deeper inverse composition and cost-to-find. It makes the algorithm more efficient in the computation, and it also helps you learn the features with a bigger receptive field. We first evaluate our method on the 3D object motion estimation using a synthetic dataset we rendered. On the unseen object with random motions, our method, highlighted in the color green, can achieve the lowest alignment error compared to baselines using either learning or long learning. We also evaluate our method on the task of visual odometry using the RGBD Tume dataset. Compared to the RGBD visual odometry baseline, which also uses a classical Lucas-Canali algorithm, our method performs significantly better in terms of various testing trajectories and also under different motion magnitudes. Our method is not only accurate, but it is also very small and fast. Compared to a baseline algorithm using a convolutional network to regress a pose iteratively, our network uses orders of magnitude fewer parameters and can achieve fast inference on a commodity GPU. In this work, we have taken a deeper look at the inverse composition algorithm by reformulating with three learnable modules. Our proposed solution is learnable, accurate, small, and fast in inference. Thank you for attending my talk. Please check out poster 136 and welcome to ask questions.
Good morning, I'm Houwen from Microsoft Research Asia, and today we are talking about Siamese network on video tracking. Recently, Siamese networks have drawn great attention in video tracking because of their fast speed and good accuracy. However, the backbone network used in Siamese trackers are relatively shallow, such as AlexNet, which does not fully take advantage of modern deep neural networks. So in this work, we investigate how to leverage deeper and wider convolutional networks to enhance tracking accuracy. One straightforward idea is to replace the shallow backbone with deeper networks, like VGG, Inception, and ResNet. Very surprisingly, this straightforward replacement does not bring much improvement and even cause performance drops. This phenomenon goes against that increased network depth and width is beneficial for elevating model capacity. So we'd like to study the underlying reasons. One intuitive reason is that these networks are primarily designed for image classification tasks, where the precise localization of the object is not paramount. We further investigate the concrete reasons. First, we observe that if the Siamese network contains padding, then the performance will drop significantly. For example, in VGG, it drops 6 points, while in Inception, it drops about 5 points. Let's analyze why does padding cause performance drops. Here, E is an exemplar image, while A is a search target, and B is the target with a shift. For Siamese network without padding, the learned representation of region A and B will be identical. However, if the network contains padding, the received field will be larger. In this case, the same content region A and B will get different representations, because one sees the padding pattern while the other does not. So it causes performance drops. We call this phenomenon as the perceptual inconsistency in Siamese networks. Moreover, we found that the size of received field and feature map also impact the tracking performance. Also, Siamese trackers prefer a relatively small network stride, which is more precise in optical localization. Based on the analysis, we summarize 4 guidelines for Siamese network design with respect to stride, received field, feature size, and the perceptual inconsistency. Then we design new network architectures and increase the backbone depth and width. Our design is built upon residual units. To solve the perceptual inconsistent problem, we augment the residual unit with a cropping operation to remove zero patterns. Moreover, we redesign downsampling residual units to reduce the spatial and channel size of feature maps, while keeping the information intact. By staking the proposed cropping inside the residual units, we build up deeper and wider networks. The construction follows our design guidelines. First, we determine the network stride. Then we stack residual units. Also, our design controls the size of the received field and output features. As the table shows, we provide 4 deeper network architecture and 2 wider network architectures based on the Inception and ResNet structure. Then we apply the designed backbone to 2 representative trackers, Siamese FC and Siamese RPN. In both Siamese FC and RPN, we replace the original 5-layer AlexNet with our designed backbone and keep other settings the same as the original framework. We can see that on ODP datasets, the wide res inception structure get 4 to 6 points improvements, while on OTP datasets, the deep ResNet achieves 5 to 6 points gains. Moreover, compared with other state-of-the-art methods, our Siamese tracker with new designed backbone achieve competitive performance. Our backbone network are lightweight and guarantee the real-time speed in tracking. Here we show some visualization results to show the robustness of our tracker. Now the code of our tracker are publicly available. Welcome to our post for more questions and details. Thank you.
Okay, So we now have questions if you have a question for the speakers for the about 3 talks, please come to the microphone. So we have one microphone here and one microphone there.
Hi, thank you. Very nice papers. It's great to see how the deep networks really improve things in difficult conditions. For a lot of these tasks, the original classical techniques focused on using very few computations per pixel. Like the classic Lucas Canade was optimized down to basically 2 pixel differences in a gradient. And so you could count the number of operations as maybe a half dozen floating point operations per pixel. With these networks that have millions of parameters, and all 3 of your techniques use deep networks with lots of convolutions and so on. What is the relative amount of computation per pixel? Is it hundreds of operations, thousands of operations per pixel? I just want to get a sense of how much slower these things are if you're counting raw computation.
Just can I ask, is to which specific paper or to?
Well, all of you, because all of you are using networks. So if you basically said, for my paper, how many floating point operations per pixel do I think I'm using?
I think I will just start from mine. So I think it's a great question, and I think it's really a great design choice we should be careful about when we're choosing specifically for these tracking problems or things like that. And for my case, and one of the very important design choice we want is to minimize the size of a network and want to learn the minimal information that actually can support you to basically and also it may actually help you to generalize, but just kind of like to learn the minimal number of ways and so that you can do this task like wonderfully. So in our task, we basically choose a very small network. So you see why we have a significant drop in the number of weights. And I think how to benchmark for example, the floating point operations and per pixel and all stuff. I think so far we haven't investigated possibly the correct benchmark to do this in the long term. But I think it's a great question that maybe we should be more careful about using this benchmark and to evaluate the efficiency of the network and maybe also how you generalize in the future. Yeah.
Okay. If there are any other questioners, I don't want to take the whole question period. Otherwise, I'd like to hear from the other speakers. Go ahead, then. I just didn't want to take the whole question.
Do you have a quick response?
The quick question is, what do you think is the floating point load of your algorithms? And the way to measure it is not gigaflops on a GPU, but just per pixel, how many operations are you doing? Do you have any idea, or is that something you'd have to compute later? I'm happy to take this question offline, so thank you very much for your talk.
Okay, so let's take this question offline. Let's thank the speaker again.
Good morning. I'm presenting facial performance tracking. In existing approaches, a high-fidelity 3D face model has been developed by encoding a highly detailed texture and 3D geometry. However, the multi-view image stream is the main requirement, which is not applicable to the mobile capture devices. So we address the following research question. Can you use a monocular video to render a high-fidelity model from unconstrained domain without any labeled data? So we present a new method that can adapt a high-fidelity 3D face model to an unconstrained monocular video. Given existing approaches with the latent representation of 3D face model, we develop a new encoder that takes a monocular image and then regress the latent representation such that it can match to the rendered scene. More specifically, our encoder is composed of 2 feature extraction modules that are responsible for converting a monocular image to the visual feature and landmark features. And the extracted features are combined through the skip connection such that we can consider the global and local features at the same time. And finally, these features are then regressed to the latent representation of the 3D face code and head pose parameters. And our encoder is initially trained by lab control dataset, but here is a problem. The visual differences between the lab control data and real-world imagery produces a significant visual artifact such as pose tracking instability. Also, due to the different lighting condition, the output appearance model is not reflective of input testing scene. So we bridge this gap by introducing a new self-supervision approaches based on the temporal texture consistency. For example, given an image at time t, we can synthesize unwrapped online texture using the predicted geometry. Our assumption here is that this online texture should be consistent across the time, and it is enforced by minimizing the texture differences between the time consecutive instances. We also adapt our appearance model to the input testing scene such that we allow the render phase to be more reflective of input phase image. To do this, we further train a 3x3 color correction filter in an online manner by enforcing the texture consistency between the adapted appearance model and unwrapped online texture, which is synthesized from the input phase image. For this, we minimize the texture error, which is made by the pixel level, the color differences between these two textures. This slide shows the comparison of with and without self-supervision, indicating that our method mitigates the domain gaps. For example, the prediction of head pose and geometry is much more robust and stable after the self-supervision. Also, due to the color correction filter, the output appearance model is adapted to the input testing scene. We compare our method with 3 baselines, which are using the key point and vertex coordinate projection and texture regression map. And we measure the performance based on the reprojection error and temporal instability. Even without adaptation method, our method shows the better result than other baselines. And our adaptation method further enforces the stability on the facial performance tracking. And due to the nature of our high-fidelity 3D face model, our method looks much more photorealistic than other baselines. And we can visualize with head pose for the facial performance tracking. And we can do the multi-view rendering from a monocular video captured under the unconstrained environment. And thanks for attention, and please find us at poster session.
Hi, I'm Raymond from University of Illinois, Urbana-Champaign, presenting the paper Diverse Generation for Multi-Agent Sports Game. This is a joint work from my collaborators Alex, John, and Kevin. We're interested in generating and forecasting of trajectory for sports games. To model sports games, we're given a dataset of game segments, such as the one shown below. The goal is to model and sample from P theta to X. More formally, we denote a game segment as an unordered set of agent trajectory, X sub k, where k is the number of agent. An agent trajectory is an ordered tuple of 2D agent position, X sub kt, which is in R2. To model P theta of X, we'll need a vector representation. Consider an example with 3 agents, red, green, and blue. We can stack the representation of these agents into vectors in either of the following orders. Which one should we use? Let's say we pass the first vector through a deep net and get the output of green, red, blue triangle. One would naturally expect for the second vectors to get the output of red, green, blue triangle, as both vector representation is the same underlying game segment. This property is called permutation equivariance, meaning that the permutation applied at the input results in the same permutation at the output. Deep nets generally do not guarantee this permutation property. However, graph neural networks do. At a high level, a graph neural network starts with a feature vector vi for each of the node. It then computes a feature vector eij for each of the edge based on the nodes. Afterwards, it sends these edge feature vector as messages to the nodes to compute the final output vector, OI. The message passing operation can be characterized by its edge to node and node to edge operations, as illustrated here. Observe that the edge feature vector is computed for all edges, and the summation operator is invariant to the node ordering. The overall representation is permutation equivariant. Therefore, to model a generative model for multi-agent sports games, we use graph neural network to get a consistent representation. We use variational autoencoder to get a sampling capability, and we use recurrent neural network for temporal modeling. Combining these approaches in various ways, we naturally get the following ablation: an RNN, a variational RNN, a graph variational RNN with diagonal adjacency matrix, where the agents are modeled independently, and our proposed graph variational RNN with a complete graph. Our proposed graph variational RNN consists of a shared RNN across all agents. However, each of the agents has their own independent hidden states. To model the relationship between these agents, we use graph encoders and decoders to learn the parameters of the following distributions. We use a latent variable z for each of the agents following Gaussian distribution. Internally, our model learns the offset of the agent position by adding the past position to the decoder's output. For more details, please refer to our paper. We obtained the following results on modeling basketball games. We considered two metrics: the L2 error on forecasting the position of all agents, or on forecasting the position of the ball conditioned on all other agents. We observed that paying tribute to the equivariance property lead to better performance L2 overall, and modeling the relationship between the agents lead to better performance on the conditional generation task. We further analyze our approach by visualizing the player velocity and acceleration through box plot. Observe that our proposed approach matches the ground truth more closely. Here we show some qualitative results of the offensive players and the ball. The ball is highlighted in orange. Observe that our approach generated a realistic ball pass. However, for the baseline methods, the ball and the player simply diverge. Here we show a counterfactual experiment. We want to know what will happen if player A passed the ball to B instead of C. Therefore, we modify the ground truth trajectory of the ball and observe which of the prediction changes. Here, each of the column is a generated prediction from the corresponding model. Observe that the player reacts more significantly to the change in the ball trajectory for our proposed GVRN4. To learn more about our work, please come to our poster, number 139. Thank you.
We present a method that jointly does tracking and detection of 2D pose of multiple people at over 30 frames per second on a single GPU. Our motivation was to build a method that is robust and invariant to input frame rate, motion blur, handling extreme camera or subject movement, and the number of people in the scene while maintaining a high accuracy. To do this, we look at some prior work. Mask RCNN and open pose were two efficient ways to extract pose using the benefits of ROI pooling or body part level extraction respectively, but had no tracking capability built in. The current top performer on the post-track benchmark yields the best results, but requires extracting body pose individually from detected bounding boxes and requires solving a spatio-temporal graph over time. Pose flow achieves competitive results as well, but requires pose detections to be done, followed by tracking sequences being built after. Detect and Track propose some interesting work on regressing tubes of bounding boxes over subjects. And on the other spectrum, LSTM pose machines demonstrated the computational benefits of recurrence, albeit for a single person, while joint flow demonstrated prediction of flow fields across key points, albeit not in real time. Now on to our method. We encode body parts as Gaussian heat maps, connections between joints as path affinity fields, and connections across people as temporal affinity fields, such as across key points, or in this case, across limbs. Our images are then fed into a feature extractor recurrently. Path affinity fields are predicted from this and the previous path. From that, key points are predicted in a similar manner, followed by temporal affinity fields. Jointly, we call this staff or spatio-temporal affinity field. Finally, we use this information to solve a frame-to-frame spatio-temporal graph across all the people detected in the scene in a real-time manner. During training, we unroll the network and train it on single images followed by video sequences. With recurrence, we achieve significant computational savings with more consistent detected poses across frames, especially seen in the heat maps detected below. One can observe it for this sequence as well. For large motions shown on the left, both key point TAFs and limb TAFs are able to track body parts across time. But with negligible motion shown on the right, key point TAFs become noisy or non-existent, forcing us to use various nearest neighbor thresholds for different scales. With limb-level TAFs, however, negligible motion simply means the TAF collapses into a PAF. Here we have an example, where the nearest neighbor cost is disabled for key point TAFs. As you can see, the poses in the bottom row with limb TAFs are significantly more stable. To solve the spatio-temporal graph for a new frame and extract pose IDs, we use the transitivity term, where omega represents a dot product between the key points and the staff field. So here's an example. Let's say we're building a person, and we're not sure if A is connected to the wrist E or B. We can sort the temporal affinity field and select the one with the highest score, and test B to C. We know that C to D is an existing tracklet, and we know that D must connect back to A. Now we can sample this staff field. Alternatively, if we go from A to E, E to F, F to G, and G back to A, we will see that we will have a lower score. This way we know that AB is the truth, and it's connected to the ID that belongs to CD. We do experiments where we simulated low frame rate cameras such as 6, 12, and 24 Hz. On the right, we tested the accuracy against a baseline KLT method, and we observed that the TAFs are able to outperform Lucas Canade, especially with large motion brought about by the lower frame rate. On the left, we have a subset of the validation dataset, and the results show that we were able to outperform the non-recurrent approach with better accuracy to computation ratio. Although a lower frame rate camera yields lower accuracy, increasing the number of recurrent stages boosts the accuracy back to high frame rate levels. Our method is currently the fastest and most accurate bottom-up approach for 2D human pose tracking, demonstrating the high accuracy to computation ratio. Here are some, the code used to generate these sequences can be found in our project page and will eventually be merged with the open pose library. Thank you for your time.
Time for questions. If you have any questions, please come near to the mic, either left-hand side or right-hand side. There are no questions. I believe we can move to the next speaker. Let us thank all the three speakers once again. Thank you.
Good morning, I'm Riccardo Specialetti from the University of Bologna. In this work, we introduced G-frames, a novel local reference frame construction for 3D mesh and point clouds. G-frames are based on the computation of the intrinsic gradient of a scalar field defined on top of the input shape. Computing correspondences between 3D shapes is a key task both in computer vision and graphics. Effective pipelines addressing this task rely upon the definition of a compact representation of the local geometries of shapes. Such point descriptors are expected to be compact, local, and distinctive. Descriptors computed on points belonging to different shapes can be matched by the Euclidean distance in the descriptor space in order to build correspondences. Local reference frame methods can be divided into two families, which relies on either covariance analysis or geometric attributes. Therefore, none of the previous proposal is similar to our approach. Given a point cloud or a mesh representing a 3D shape, for each point we compute a local reference frame, which is a system of Cartesian coordinates which endows descriptor, such as, for example, shot, which we will use in our experiments with pose invariants. In these pictures, we show local reference frames computed on points on a 3D shape. As descriptors are computed relatively on the local reference frame, their effectiveness depends on the repeatability of the underlying local reference frame. In these pictures, we show local reference frames computed on corresponding points of two shapes. Our proposed local reference frame is based on gradients of scalar function defined upon the input shape. The gradient for a given point P is computed as the average gradient of its neighboring points. We then project the computed gradient onto the plane defined by norm at point P and rescale the projection to unit norm. The final local reference frame is obtained as follows. X-axis is the projected gradient, Z-axis is the norm at point P, and final Y-axis is the vector product between Z and X-axis. The choice of scalar function determines the invariance provided by the local reference frame. In this work, we have experimented with the function listed in the slide. As for the repeatability, in this picture, we show how the chosen function is highly repeatable. Our method can effectively deal with strong differences in point sampling and with increasing surface noise. We show results dealing with rigid shape matching. In these experiments, we use the 3D Stanford scanning repository. We show in this slide the scalar function used for our experiment, mean curvature, sum of tutorial equidistance, and flare function. We use the shot descriptor equipped with either its original local reference frame or our proposal. The repeatability of our local reference frame is evaluated using the standard metrics adopted in literature. Our proposal with Z and flare function exhibit best results. Also in the descriptor matching, our proposal outperforms the original shot. As for the formable shape matching, we use the mean and Gaussian curvature like in the previous rigid setting, alongside with two additional functions designed for this specific task, discrete time evolution process and feedback vector. In this slide, we encode the heatmap. With the heatmap, the point-wise matching errors on Faust's dataset. We show that G-frames allow for more accurate descriptor matching. Similar consideration applies to the top kids dataset. In this slide, we show quantitative results obtained following Princeton protocol. Again, our proposal yields clearly the best result, in particular when using the function specifically designed for non-rigid shape matching. Thanks for your attention. For further details, come to our poster.
Hello, and welcome to my presentation titled Eliminating Exposure Bias and Metric Mismatch for Multiple Object Tracking, which is a joint work with my advisor, Pascal Foy. So let me break down the problem. Traditionally, in multiple object tracking, one of the most frequently used primitives is a pairwise potential, which tells us whether two detections belong to the same person or not. It could be posed as a classification or as a distance learning task, and it is typically trained on pairs or triplets of detections. It is a very natural thing. Now enter a new world where we have enough data to reason on the longer time frames, and we can use sequences of detections. So the question is, how do exactly we use those sequences? Well, the easiest way is to do exactly the same as in pairwise case. Ask the question whether two sequences of detections belong to the same person or not. However, this comes with a number of problems now. First one is that during inference, should your model make a mistake, you're asking a question whether this mix of 2 people is the same as this mix of 3 people or not. This is referred to as exposure bias, wherein your distribution of training and inference data doesn't match. Furthermore, this question just doesn't make sense in general, which is to say that maybe classification, posing it as classification task is not the most reasonable idea. And if you wanted to reduce the exposure bias by training on all possible pairs of sequences, well, first of all, that would be computationally infeasible, and that would have actually a large class imbalance. So these are the problems that we're trying to address here, and we're trying to address them by answering 2 questions. What is the measure of a goodness of sequence of detections, and how can one learn to predict this measure, given that there are combinatorially many possible sequences, but would like to reduce the exposure bias. So we want our training and testing distribution to be the same. Let's start by answering the first question about what is the measure of goodness of a sequence. Ideally, we would like such a measure of goodness that reflects the target tracking metric that we care about. And so what we're trying to do is to reduce the metric mismatch, which is with mismatch of training and inference metric, by learning to predict the IDF metric. Traditionally, IDF is computed between a trajectory and a ground truth. Unfortunately, during inference, ground truth is usually unknown. So we actually need to predict the components of this metric that are unknown. That is, intersection over union with the ground truth, and predicting whether the ground truth exists at all. And we do that with a single layer bidirectional LSTM, which for every frame in a sequence predicts this intersection of reunion and whether the ground truth exists, which allows us to compute the approximation of the IDF metric, thus reducing the metric mismatch. Now that we have learned this metric, how can we actually learn it? Well, we do something similar to a technique called Dagger or data aggregation, where starting with the untrained model, we run multiple hypothesis tracking, and then we get some sequences, which we add to our training data, and we do a step of training on this data. This iterative procedure allows us to expose the model to its own mistakes, and therefore reduce the exposure bias. And the good thing about multiple hypothesis tracking in this case is that all what we need is just the comparison between 2 sequences, which one is better, which is exactly what our model provides. So given those 2 components, our metric and how we train it, what are the actual results? Well, we have 2 versions of our model, one that uses appearance features and one that uses actually purely geometric features, that is coordinates of the bounding boxes. And with the appearance model, we achieve state-of-the-art results in terms of IDF metric on several data sets, but here are 2 most interesting findings. First one is that our metric that uses simply geometric features is able to outperform baseline methods that use appearance on the Duke MTMT-C data set. And second, if you look at the top left, you can see that there is a strong negative correlation between the IDF and MOTA metrics. And we have actually made a synthetic experiment to show that these 2 tracking metrics are actually disagreeing in some case. So to sum everything up, here are the several takeaways. First one is that if you're training a sequence model, what you might be interested is using regression instead of classification loss, and you might consider enriching your training data by iterative training inference to expose it to the errors. Second is that there is actually a large margin between how our model is trained and what could be achieved, and simple geometric features are surprisingly powerful. Third is there is a significant trade-off between MOTA and IDF tracking metrics, and if you'd like to know more, come to our poster number 142. Thank you.
Hello everyone, I'm Junyu Gao. Now I'm gonna to introduce a visual tracking framework using graph convolutional networks. And this is a joint work with Professor Tianzhu Zhang and Changsheng Xu. The goal of visual tracking is to estimate target state over time. As we know, it is very challenging for visual tracking in the real world. It is due to the occlusion, changes in illumination, scales, and fast motion. Recently, with the powerful deep network and large-scale labeled video frames for offline training, Siamese-based trackers achieve favorable performance and efficiency. One notable example is SIAM-FC tracker, which learns a matching function in an embedding space and wins the VOT 2017 real-time challenge. However, Most Siamese-based trackers has two major issues. First, many of these trackers only use the initial target template from the first frame to match candidate patches without considering the spatial-temporal information. Second, these trackers do not leverage the surrounding context of the target object for getting the adaptation of target appearance modeling. This is a not good choice. So, inspired by the above observations, we propose an end-to-end graph convolutional tracker, GCT, based on the SAM-FC method, which can jointly consider both the spatial temporal information and the target context information of the current search image. SAM-FC learns a similarity function f to compare an exemplar image z to a search image x in a learned convolutional feature embedding space phi. We then design a graph convolutional transformation, phi GCN, into the Siamese architecture to jointly consider the spatial temporal appearance modeling, that is zt minus upper t to t minus 1, and with the context information of the current search image xt. The graph convolution is a linear transformation as the multiplication of the graph signal x with the filter w under the graph adjacency matrix A. However, learning phi GCN is not efficient, since it suffers from high computational burden for modeling the message passing between current context information xt and each of the historical exemplar embeddings zts. To reduce the computational cost, we further decompose GCN into two sequential graph convolution modules named spatial temporal GCN ST GCN phi 1 and the context GCN CT GCN phi 2. In the offline training stage, the loss of an exemplar's instance pair is generally represented as a logistic function. We use videos from ImageNet VID dataset for model training. After offline training, we use the network for testing directly without fine-tuning. This is our pipeline. For the historical exemplar images, we use ST-GCN to generate the ST features with a spatial temporal graph. Then, the generated ST feature is combined with the current context feature to produce an adaptive graph, which is used by the CT-GCN to produce the adaptive feature. This feature is evaluated on the search image embedding via a cross-correlation layer for target localization. We use multi-scale patches to estimate the scale of the target. Next, we will show the experimental results. The results on 4 datasets, OTB, UAV, VOT 2017, shows the favorable performance of our tracker, and our tracker achieves the real-time speed. The ablation results also show all the components in our framework are useful. So for more details, please come to our poster. The number is 143. The project page of our GCT is here. And any question, please contact me. Thank you very much.
Okay, so we have time for a couple of questions. If you have questions for the about 3 speakers, please come to the microphone. Okay, in the meantime, I have a question for the second, is that the second? Okay, for the second speaker. So it's interesting to see just using geometry features, you can achieve like a good results. I'm wondering what's the limitation for that. For example, you can think about if you have a video in the training set and in the testing set, you have video with different frame rate, then you will produce sequence with very different statistics. So how would this type, how will you could you comment on how do you handle those kind of mismatch?
So you mean if you were to train on a sequence with 1 frame rate and
Right.
evaluate on the sequence? Well, so in our work we didn't address that, but you can always kind of sample it more or less to have the same frame rate. So we actually, so even though on the, we had kind of this is up to 60 FPS, we actually used for DukeM TMC FPS of 3. So in that sense, kind of, you can use it in a more or less large range. So if it was not 3 frames per second, but 4 or 2, in some range, it would still work. But yeah, if you needed to, that kind of statistic should probably match in training and testing approximately, otherwise it wouldn't work.
Okay, yep, thanks. Any questions from the audience?
So
yep.
I have a question about the graph convolutional tracking work. So basically you utilize a Siamese network which consists of 2 branches. One is the template branch and another is Zhipeng. So here I can observe that you have changed the template branch from initial frame to the historical frame. So do you have some consideration of appearance variation which causes the drifts, the target drifts, which leads to noisy updates of the template branch? So do you have such kind of consideration to reduce this effect?
Yeah, we consider, we mainly consider 2 types of informations. The first is the spatial-temporal information. This is about the historical example images. Yeah, we use the spatial-temporal structure of the target to learn a more robust target appearance model. And the second information we used is the current search image. Yeah, we think this can provide us an adaptive information to get the target appearance adaptation for the current frame. Yeah, so this is what we major consider. Thank you.
Any questions? Okay, so let's thank the speaker again.
Okay, good morning everyone. I'm Gautam Bhatt and I will present our work, Atom, Accurate Tracking by Overlap Maximization. This is a joint work with Martin Danelian, Fahad Khan, and Michael Felsberg. So, do we need more accurate tracking? To find out, let's look at the results of a recent state-of-the-art tracker, UPDT. From the videos, we can see that UPDT is fairly good at localizing the target in the image. However, the quality of the bounding boxes is poor. So in this work, our goal is to improve the accuracy in the state-of-the-art trackers. To find the reason for the poor accuracy, we look at the tracking by detection pipeline employed by many trackers, including UPDT. So given a video sequence with annotation in the first frame, this approach is learn a classifier to distinguish the target from the background regions. Next, the classifier is applied at different scales on the test frame to obtain score maps. The location and the scale which obtains the highest score gives us a new target state. As you can imagine, this strategy works fine when the target undergoes simple scaling. However, how about the cases when there are rotations or deformations? As we have seen before, the strategy struggles in these cases. Okay, and the projector struggles as well.
Just about a minute. We'll be back soon. So the machine on which the video was running just got restarted. So it'll take a little while. We'll be back soon.
Okay, so you have to listen it again. Okay, so we'll look at the tracker failing once more, and I won't say much now. Okay, so to find the reason why the tracker failed in the previous sequence, we look at the pipeline employed by these trackers. So given a video sequence with annotation in the first frame, the trackers train a classifier to distinguish the target from the background. Next, given the test frame, they conduct a multi-scale search to get the score maps, and the location and the scale, which obtains the highest score, gives us the new target state in the current frame. As we can imagine, this strategy works fine when the target undergoes simple scaling. However, how about the cases when there are rotations or deformations? We have seen twice that the tracker fails in these cases. So in order to effectively handle these scenarios, the tracker needs to have a high-level knowledge of the target object. For example, it should know what constitutes an object boundary. Unfortunately, such a high-level knowledge cannot be learned from a single image. Thus, in our approach, we aim to learn a generic object representation offline, which we can then utilize for a bounding box estimation task for any arbitrary object online. Our approach is inspired from the recently introduced IUU-Net for object detection. So given an image with a proposal box, IUU-Net predicts the overlap between the object and the given proposal. The key idea is that the IU prediction is differentiable with respect to the proposal coordinates. Thus, we can refine the proposal by maximizing the IUU. Compared to the naive multi-scale approach, using a class-independent IUU-Net provides a decent improvement in tracking performance. However, in tracking, we also have the annotated target appearance from the first frame, which we can exploit to get more accurate IUU predictions for the current target. We achieve this by using a modulation-based architecture. From the first frame, we compute a weight vector, which is then used to modulate the features from the test frame. Thus, we want to select the features which are most useful for the current target. Integrating the target information in this way provides a significant improvement of over 5% in tracking performance. So although the IUU-Net can provide accurate boxes given an initial estimate, it is not trained for the task of robust target background discrimination. Thus, for this task, we employ a two-layer network head, which is trained from scratch in the first frame using the least squares laws. Now, since the classifier is trained online from scratch, the key challenge here is how to train it fast so as to get high tracking speed. For this task, we employ the conjugate gradient algorithm with Gauss-Newton approximation. Our approach provides superior convergence as well as better tracking performance compared to the standard gradient descent method. So our final tracking loop is simple. So given a test frame, we first apply the classifier to get a coarse estimate of the target center. Next, we generate proposals from using the estimated target center and the previous target size. The proposals are then refined by maximizing the IOU to obtain the final target box. The classifier is then updated with using this new box and the new frame information. Finally, some results. On the VOT18 dataset, our approach obtains the best results, outperforming the recent state-of-the-art approaches. Further, our tracker runs at over 30 FPS. Good, so we have some nice numbers here, but how well does it actually track? Let's look at some qualitative examples. From these videos, we can see that our tracker tracks pretty well, even on challenging scenarios. Also, you can download our code from this link and test it yourselves, or visit us at our poster number 144 for a live demo, as well as for more discussions. Thank you.
Hello, everyone. I'm Dai Kenan. I come from Dalian University of Technology and supervised by Professor Lu Huchuan. I will introduce this work. We were tracking where adaptive spatially regularized correlation filters. For tracking, correlation filter is an important branch. The CF-based trackers explore the large numbers of cyclical shift net samples for learning. It has been shown that spatial regularization can help improve the performance of CF. Usually, it is a negative Gauss shift. It has two main effects. One is to limit the shape of the filter, and another is to make the filter more focused on the learning of the target center. But this kind of predefined spatial regularization has some obvious problem. If we use the predefined regularization like negative Gaussian, it will always focus on the center of the target box. That is the part close to the center of the target box. The learning of the filter is promoted, and the part farther away from the center of the target box, the learning of the filter is suppressed. But in these cases, Figure 1, occlusion, Figure 2, background clutter, Figure 3, disappearances, predefined regulation is not good, and even increase the risk of filter drift. Therefore, we propose an adaptive spatial regularized correlation filter model. This is our objective function. H is the filter that needs to learn. W is the adaptive spatial regularization. It is a variable and is also need to learn. Y is a Gaussian lab. X is a feature of training samples. P is a binary matrix. WR is a reference weight. Our IS or CF is a general CF model, and the well-known KCF, SRDCF, and BACF algorithms are its special cases. For example, if W is equal to identity matrix lambda R equal to lambda 2 equal to 0, it is BACF. Here is the visualization of our adaptive spatial regularization. For each pixel, a large value of the adaptive spatial regularization will give a great learning penalty of the filter at this pixel. From the first sequence, we can see that when there is a background clutter inside the target box, only the pixels with a clear target, the penalty for the filter learning is small. And another example is about the disappearances. When the target exists, the overall value of the spatial regularization is very small. Once the target disappears, its overall value becomes larger. When the target reappears, its value becomes to shrink again. For scale estimation, the previous CF-based tracker usually applied the learned filters on multi-resolution of the search region to estimate scale changes. However, it is very time-consuming to extract multi-scale deep features. In this work, we attempt to learn two CF models. The location CF model is trained on a sum of deep features and shallow features, use adaptive spatial regularization. And although this extension process of this CF model is time-consuming, it mainly requires to be extracted on one scale during the tracking process. The scale CF model is trained on the shallow features. This is our performance. On OTB 2015, our methods can achieve an IUC score of 0.692. This is our performance on temporal color 128. And this is the result on VOT 2016 and VOT 2017. In this table, we summarized both accuracies and speeds of top 5 tracks on OTB 2015. Our approach can meet real-time requirements on the GPU. Finally, you can find the code on my GitHub. If you have any other question, you can contact me by email. Thank you.
Hi, hello everyone. I'm Yaadhav Liu from Michigan State University. Today I'm going to introduce our work, Deep Tree Learning for Zero-Shot Face Anti-Spoofing. Face recognition systems are widely used in our daily lives. Most of the systems take an RGB face image, match with the correct identity, and grant the access to the user's account. However, the attackers were trying to hack into the user's account by presenting the target's face on material such as digital screen. The system cannot distinguish the liveness of the input face, which can lead to a security breach. To protect the system, face anti-spoofing techniques serve the exact role by detecting the source of the face before performing any recognition and matching. There are many challenges in handling face anti-spoofing, such as illumination, pose, and sensor variation. However, among all the challenges, unknown attacks are the hardest one, but the least to be studied. Imagine your face anti-spoofing system is well-trained with those screen attacks. But if an attacker launches a mask attack, the system may still suffer from severe failure. We regard the detect of unknown spoof attacks as a zero-shot face anti-spoofing problem. But before we dig into any details of our methodology, let's first take a look at the data. Here we list the commonly used face anti-spoofing datasets. As we can see, none of them include more than 3 types of spoof attacks. Such datasets cannot provide enough diversity for a comprehensive study for this problem. Therefore, in this work, we propose a new database called SIWM that includes 13 types of spoof attacks to advance the study of this problem. Specifically, we include 5 types of 3D mask attacks, 3 makeup attacks, 3 partial attacks, and print-to-replay attacks. To fully leverage this database, we adopted the leave one out testing protocols where each time you leave one spoof out as unknown and train with the rest of them. Back to the method, we noticed several limitations of the previous research. The first thing is the limited spoof types as we just discussed. More importantly, those methods only model the distribution of the true face and detect the unknown attack as anomaly. We believe if we can learn a semantic embedding from the known attack to represent the unknown, we can get a better zero-shot performance. Therefore, we propose our deep tree neural network. It consists of normal convolution layers, tree routing units, and supervision in the leaf nodes. When a data comes, the routing unit will decide a value to guide the sample to go left or go right. At the leaf node, the network will perform a supervised classification task and a binary mask regression task to learn the difference between live and spoof. Showing below, the binary mask indicates pixels that belong to the spoof material. The tree routing units are designed to find the most significant difference of the incoming data in an unsupervised fashion. We only consider the difference among the incoming spoof, such that a split at each tree node will represent a spoof attribute, such as a partial attack or a global attack. In the end, we're able to learn several semantic attributes to cluster the data into subgroups for fine-grained zero-shot detection. Formally, the routing units can be described as a projection to a base vector V. Based on the eigenanalysis, the larger the eigenvalue is, the more variation we can have on the base V. Hence, we just need to maximize the eigenvalue to achieve our goal. In the experiment section, we evaluate our proposed method on the leave-one-out testing protocols and compare with the state of the art. Our deep tree network has a significant improvement on both average classification error rate and equal error rate. To visualize the embedding, we use the protocols where the print attack is unknown. As we can see from the testing result, our printer attack can be represented by the attribute from replay attack, paper mask, and funny eyeglasses. To summarize in this work, we first handled the wide range zero-shot face anti-spoofing. We proposed a novel unsupervised approach to learn the hierarchical attribute embeddings, and we achieved the state of the art. Please come to the booth 146 for more details. Thank you.
We have some time for questions. So if you have questions, please come to the microphone. There are 2 microphones, one on the left-hand side, one on the right-hand side. In the meanwhile, I have a question to the last speaker. I saw your error rates, ECER and EER. I find they are in double digits and pretty high, especially for the deployment. The error rates, EER and ECER, 11, 16, like you have in double digits. Is, I believe they are pretty high, and if somebody would like to deploy, it's going to be a challenge. So
that's correct. So because the attack we are trying to predict is unknown, we have never seen them in the training set. Right. So for sure, it will be higher than, for example, if you see them in like normal traditional anti-spoofing, you see them in the training set. So that's the problem we're trying to attack. We're trying to see how much we can get the immersion from the known attack. But compared with the previous method, which is a still valid in the traditional anti-spoofing, our method have a huge improvement to detect more spoofs. Yes.
Thank you. You have questions, please.
Hi, I have a question for the first 2 tracking authors. So currently, in the tracking community, people use this bounding box as a localization for a target object. It works well for those rigid objects like faces, cars, and buses. I'm wondering, but you show examples, for example, the figure stating that those kind of articular objects and highly deformable objects, I think that bounding box localization may not be that accurate to localize an object. So do you think, can you share your kind of comments on how the method could be extended to more precise localizations?
I guess right now there are already lots of work on getting a segmentation mask out as well, instead of just a bounding box. And yeah, I guess even from here you can get like some coarse attention map, so that which you can use as an auxiliary information for obtaining the bounding box. So I think, yeah, there are more and more works which provide a segmentation mask.
Okay, thank you.
We have one last question. Yes.
I have a question for the second talk. How do the adaptive filters respond to noise?
We optimize the correlation filters and the spatial regulation at the same time. The spatial regulation can learn the part if can distinguish the part it is not target or not. If it is target, its parameter is very low. If its noise, its parameter is very high.
So okay, this will end the QA session. So let us thank our speaker once again.
Hello everyone, my name is Jiankang Deng from Imperial College London. ArcFace is a joint work with Jia Guo, Nian Nanxue, and Stephen Zabilu. The main target of face feature embedding are intra-class compactness and inter-class discrepancy. Triple loss employ margin to achieve those 2 targets at the same time, but the image-to-image comparison is difficult because there are too many pairs. So why not change image-to-image comparison into image-to-class comparison, as class number is much fewer than image number, but online class feature embedding is not very efficient. In fact, in image-to-class class comparison is very efficient in softmax loss, but in the original softmax loss, there is no margin. Based on those observations, we proposed our method named ArcFace, which has extensive image-to-class comparison as well as margin. There are 2 main steps. The first step is X and W normalization, which turn the similarity score into cosine similarity. The second step is incorporating active angular margin. The illustration figure and the equation as well as the code are exactly correspond to each other. So ArcFace is very easy, only needs several lines of code. ArcFace is also explicable. From the view of softmax loss, ArcFace can enlarge the design margin, angle, arc, and geodesic distance are correspond to each other within our solution. From the view of triple loss, arc phase change image-to-image comparison into efficient image-to-class comparison. Compared to sphere phase and cosine phase, arc phase has different design margin and different target logic curves, and those slight difference improves the performance. Arc phase is very efficient. Even though W is large, we can easily split it into different graphic cards. Arc phase is effective. We obtain self-art performance on many benchmarks. Arc phase is also enlightening. It can be improved, extended, and used in some related works. We released everything to facilitate future research. Now we show a video demo to check the strengths of arc phase and the bad case of arc phase. This is an identity search demo for the detector. Why it is stopped? Okay. Sorry about that.
So the laptop where the video was running is just got restarted, and we will take about a minute. So please bear with us. Thank you. We're almost there.
Hello. So I will repeat the slides again. So the motivation of deep face recognition are intra-class competence, and the targets of face recognition is intra-class competence and inter-class discrepancy. Triple loss has the margin, but image-to-image comparison is difficult as the image numbers are very large. We change image-to-image comparison into image-to-class comparison as the class number is much fewer. In softmax loss, image-to-class comparison is very efficient, but there is no concept of margin. So we know that extensive comparison and margin are very useful for deep face recognition. Based on those observations, we propose the arc phase, which has extensive image-to-class comparison as well as the margin. So there are two main steps. The first step is X and W normalization, which turn the similarity score into cosine similarity. The second step is incorporating active angular margin. Arc phase is very easy, only needs several lines of code. ArcFace is explicable. From the view of softmax loss, ArcFace can enhance the DC margin. The angular margin is exactly corresponding into arc and geodesic distance. From the view of triple loss, ArcFace change image-to-image comparison into efficient image-to-class comparison. Compared to sphere phase and cosine phase, ArcFace has different descent margin and different tactological curves. Those difference improves the performance, obviously. ArcFace is very efficient, even though the W is very large, but we can easily split it into different graphic cards. ArcFace is effective. We obtain state-of-the-art performance on many benchmarks. ArcFace is also enlightening. It can be followed, extended, and improved, and can be employed in some related research. We release everything to facilitate the research. Now I show a video demo which touches on searching 6 identities within the whole video. The detector used here is named retina face. It can output a detector box, a detection box, and the 5 facial landmarks. We released the annotations of 5 facial landmarks on wider face within the Insight Face GitHub. The detector is also released there. So the whole system can be reproduced by using retina face and ArcFace. For each frame, we detect and normalize crop each face and use the proposed ArcFace to get the embedding feature. And we use the embedding feature to calculate the cosine similarity between current normalized crop and the 6 template. The small bar beside the face box on the right side of the face box indicates the cosine similarity. As we can see from the video, our face detector can easily handle pose variations, illumination, and the landmarks are very accurate for normalized crop for face recognition. But when the face has large pose variation and occlusion, the similarity score fluctuated, and we can find that ArcFace can handle face variations to some extent, but under some extreme challenge case, ArcFace still has space to improve. Here are some embedding results, searching results. As we can see, ArcFace can handle introvariance to some extent, but for some extremely challenging case, ArcFace is still can be improved. Beyond ArcFace, we organized a lightweight face recognition challenge, and welcome participation and paper submission. That's all. Thank you.
Okay, my name is Lin Ma. My presentation is entitled as Learning Joint Gate Representation via Triplet Loss Minimization. Gate recognition is the task of identifying people at a distance using videos of their working patterns. This is an active research topic in the field of computer vision due to its importance in real-world applications, such as video surveillance, forensic identification, evidence collection. As a behavioral biometric, gate exhibits unique advantages over the other biometric like fingerprints, iris, and face, because gate-based methods can identify subjects from low-resolution video sequences with no subjects cooperations. Most of the previous works focus on cross-gate representations, which is a concatenation of a pair of gate images and labeled to same or different as the input of the figure. While being effective in capturing the relationship between a pair of gates, these methods ignore the labels of each single gate images. Nowadays, some deep learning methods tackle the problem based on single gate representation solely. They extract a unique gate feature enclosed in a single image and then match them to predict the relationship, while this method ignores the cross-gate representations. In this paper, we developed a deep network to jointly learn the unit gate and cross-gate representations. And also, we propose an effective loss functions for gate recognition, which is to guide our model to extract powerful features with smaller intra-class variations and large inter-class differences. As the figure shows, from A to B, the proposed model additionally learns the identical unique gate representation, which enlarges interclass differences among subjects. From B to C, with the help of the proposed quintuplet loss, not only the interclass variance increases, but also the intra-class discrepancy is decreased. This is our basic framework, which is named as GUC-net, Joint, Unique, and Cross-Gate Net. The input is a pair of gates. There are 3 output branches, 2 corresponding to unique gate representation, and 1 for cross-gate representation. The proposed GUC-net is updated based on 2 kinds of the representations, and the overall function is a combination of the 2 kinds of losses, the unique loss and cross-gate loss, which is shown in these slides. The popular methods of learning the cross-gate representation are based on recognition signal, which aim to classify concatenate cross-gate representation. In order to obtain more powerful cross-gate representation, we adopt both recognition and verification signals as our supervision signal and propose a quintuplet loss. Different from traditional recognition verification loss, we define a novel quintuplet loss based on the quintuplet gates. And the slide shows the top column is the previous loss, and the bottom is our proposed loss. And based on the loss function, we extend the basic GUC-net to multi-pair GUC-net, which serves as a final framework during training. As the figure shows, a pair of gates can be combined as a whole, while the label of the same ID and different ID. 3 pairs of gates are input to extract features. 2 pairs of gates are from different subjects, while 1 pair of gates is from an identical subject. We tested them on 3 public data sets. And the rank 1 accuracy by varying the weight parameters on the validation set is shown in this slide. Based on the figures, we set different parameters in our final training strategy. In order to show the effectiveness of GUC-net and the quintuplet loss function, we reported the results of different rank accuracies of 6 models on 2 data sets. This table shows that the GUC-net and the loss outperforming the conventional SIM models. Then we compare our methods with the other several arts methods. The results in table 3 show our methods can outperform the several arts method on both data sets. Also, the issue of cross-view is crucial for gate recognition. Thus, we evaluate our methods under the condition of cross-view. The comparison indicates that our proposal achieves satisfactory performance under the cross-view protocol. And thanks. If you have any question, please drop by our poster.
Hello, everyone. My name is Zhang from Michigan State University. Today, I'm going to present a work on gate recognition via disentangled representation learning. So what is gate recognition? Here's some examples shown here. It aims to identify individuals by the way they walk under different variations like changing clothes, carrying a bag, or different view angle. There are mainly 2 types of gate representations, so appearance-based and model-based. For example, GEI is appearance-based. It uses average syllables as final representation, and 2D poster estimation is an example of model-based. Then both can be sent to classifier to perform the recognition. But the thing is, there are some issues with those methods. First, we see a huge difference of a 2 GEI if the same person in different clothes. And the second issue is that the model-based methods are very easy to fail when the person is a long distance from the recording camera. And thirdly, the frontal view has much less information than the side view in both representations here. Then let me introduce our work, GateNet. First, we detect and segment people from original video.
Then GateNet extract 2 disentanglement representations, the appearance, and gate, which is being used to perform the recognition. Here's more details. First, we get appearance and gate features from frame IT1 through the encoder. We do the same thing for another frame IT2. So appearance of IT1 and the gate of IT2 can be sent into the decoder to obtain a synthesized frame, which should be very similar to IT2. We encourage their similarity using a reconstruction loss. The purpose to disentangle the appearance gate for each of the frame. And the same encoder process another video of the same subject, but in different variation. We define gate similarity loss, which is a mean square loss on average 2 set of gate features. This loss encourages the same subject has the same gate information even different variation. And then we send the gate features to LSTM, and then output the corresponding hidden variables. Then we incrementally calculate the cross entropy loss between the average hidden variable and ground truth. For example, here we calculate the loss on average of 2 features, 3 features, until all of them. Then finally, we jointly minimize all the 3 loss functions with gradient descent method. We evaluate on 3 the most popular gate database, KSFB, OUSR, and USF. They all have large amount of subjects under different working variations like view angle, carrying backs, and changing their closes. And to encourage more research on the gate recognition from frontal view, we collect an HD frontal view gate database under 6 variations, including view angle, time, then there's a walking speed, and the carrying back, and a wearing coat, and the background with multiple people. Here, we use 90-degree as gallery and other 10 views as probe on KSFB. We compare rank 1 score with recent state-of-the-art appearance and model-based method. So GateNet has a large improvement on the 2 challenging view angle. It also outperformed the BICEP prior work. Here on FVG database, we use a normal frontal video as gallery and all other probes. Note that we evaluate the true accepted rate here. And the improvement over the state-of-the-art is very substantial. We train 2 models, one with gate similarity loss and one without. And the appearance of the original frame is better preserved, which means gate features has less appearance-related information, which is good. Here's another example. And the rank 1 score changing close variation on KSFB is compared. Yeah, here's a with the loss, and here's a without. You can see the preserved information. Here's another example. The rank 1 score, with and without our design loss. As conclusion, we propose a disentanglement learning method to learn gate representations from the RGB imagery. And thank you all. Welcome to our poster 149.
Okay, so if you have questions, please come forward. Okay, if not, this concludes our session. So thank you very much. Please thank our speaker for all the speakers for in these sections.